Let me zoom out a little
Oh,
bit.
yeah, there we go. Thank you.
Yeah. All right, any questions on the first one?
Is that number represent like how much it changed, or?
Yes, we feel like we should do, well, it's hard how to know how much to jump in right away.
Yeah, sorry.
No, it's totally fine. It's totally fine. So let me draw a picture here to try to tell you what's happening. I'm gonna mute somebody's, there's like a delay. I'm gonna mute everyone who's not talking. There's like this delay where like somebody's speaker is picking it up and then it's coming through like twice. I don't know if you can hear it, like I can hear it coming through twice. So I just have everybody muted. You can unmute and talk whenever you want to. So we're looking at the point 2, 2, 1. Hold on, there's a problem with that. Look at this example. So this is a circle radius 2, but 2, 1 is not on the circle. That's not good. It has to be on the circle. So let's call it square root of 3, 1. I apologize for that. We'll blame Dr. Sugar. It's all her fault. It's an easy mistake to make. So I'm going to change my answer then to fit that. So the x squared plus y squared equals 4, the x and y should satisfy that because so our points are traveling on the circle. And so square root of 3, 1 is right here. That's the point on the circle, square root of 3, 1. And so what we're saying is if x is increasing at a rate of 3, so that means x is increasing, x is quickly going to the right. dx dt is 3. Maybe it's per second, maybe it's slowly, maybe it's per hour, per day, who knows? We don't know what the time units are. But dx dt is increasing here, positive 3. So if x is going to that in that direction quickly, what's going to be happening to y if the point has to stay on the circle? Is y going to be increasing or decreasing?
Decreasing?
It has to be decreasing. Can you think of a good reason why, Christopher? Or like, why did you think decreasing?
Because x is stretching horizontally and y is going to be at the same point. So it'll be like more like an ellipse.
Mm-hmm. Sure. And you can see how the point, if x is going to the right, the point is going to have to move down. That's the only way to continue on the circle, is the point has to move down to stay on the circle. And so that's why we got a negative answer here. So out to the question, the response to Albert's question is it's representing that y, in order for the point to continue on the circle, if x is increasing, y has to decrease. And that's how quickly it's decreasing. Yeah. That help?
Yeah, it makes sense. Because
Cool.
concerning related rates, both are changing. So, yeah.
Yes, they're
Yeah,
related.
makes sense.
The whole section is related rates. Yep. And so what we have here is the rate of change of y is related to the rate of change of x. Yeah. Great questions. Great thoughts so far. Any other questions on the first one? All right. And again, at any point, just pop your mic off, your mute off, share a question, a comment if you want to. Type it in the Zoom chat. You can raise your hand if you recall, if you like tap your screen and then click on participants, you can like do a little blue raised hand in the corner is what it looks like to me. All right, let's try the next one. We have a point moving along the graph, y equal x cubed, such that dx dt is 1 centimeter per second. We're going to find dy dt when x is 2. Let's draw the graph of this and see if we can guess whether it's going to be positive or negative. Let's do that. Y equal x cubed. Whoops, I'm still doing red. I'm like enjoying the marker and everything more and more and more here. This is y equal x cubed. When x is 2, so I'm just going to say that's over here, 2. Well, what's the corresponding y? Since it's on the curve, what must y be equal to? This is the part, yeah, I was gonna say this is the part where you can unmute yourself and so yeah, that's right. I think, was that you, Chantel? That's all right. So that's the 0.28. And so
Sorry, I'm able to unmute.
it's all good. So dx dt is 1 centimeter per second. So now we have some actual units. So if these are centimeters, dx dt, I'm going to put an arrow to the right, dx dt is 1 centimeter per second. So given that, do we think dy dt is going to be positive or negative? Why don't you pause, don't answer, and just think for like 10 seconds. Do we think dy dt, will that be positive or negative? So the key here is dx dt is going to the right at x is moving to the right at 1 centimeter per second. Ooh, oh shoot. We're gonna do a poll. Yes, this is gonna be so cool. My first poll. Add a question. Oh, there are too many windows up now. This is not good. Okay, maybe I can't do a poll. This is gonna take a long time because it's my first one. Is dy dt This could be cool to do this if I have them all already ahead of time. Okay, save. Okay, I created a poll for this meeting. All right, now poll. Oh, it did not work. Okay, well, that's interesting. Okay, I created a poll, but then when I go to add the poll, it says you have to create a poll. So good in theory. I'll try it again next time. So what do we think? Positive or negative? Do we think it'll be positive or negative? Anyone have a thought? Oh, there are yes or no buttons in the chat. Ooh. Interesting. Positive, Alexis says in the chat. Definitely still trying to figure out some of the Zoom features here. It'd be cool if like a poll, you didn't get a poll to pop up, did you? No. Oh, Brittany, you did?
It came and went. It wouldn't
Oh,
so it'd show up and then it just timed out.
interesting. Yeah, I don't know. Okay, anyway, it looks like most people agree, at least the people are chatting. Mitch, I'm going to take a look at that. That's a good tip. That it would be positive, and you are correct, because as x increases, y will be forced to go up the cubic graph, and so dy dt will indeed be positive. So let's go ahead and find it. We're going to do it the same way we did the last one. We're going to implicitly differentiate both sides with respect to t, because that's what's changing here. The t is changing. We'll get, let's see, the derivative of y with respect to t is just dy dt. Ooh, that's a good tip too, Chantal. We could just do the thumbs up, thumbs down too. And then on the right side, we'll have 3x squared and then dx dt. Okay.
I got a quick question.
Sure, Albert.
Is the whole graph changing, or is it like the specific point changing? Or
What it is the point. So there's a point that's moving along the graph. So the graph itself is not changing. We're just imagining a point traveling along the graph. Does that help?
yeah, now I can see it.
Okay, good. All right, we're going to evaluate this. So for our answer, dy dt, we're just going to plug in some stuff here. X is 2, and then y is 1, and so we'll get 12. Here we do have some units. Let's see here. I guess we could do the units. 2 is centimeters. So this, sorry. Let me rewrite this. centimeters. The 1 is centimeters per second. So our total units would be 12. It would be centimeters cubed per second. Centimeters cubed per second. You'll get a centimeter squared from the 2, and you'll get a centimeters per second from the 1. So there's our, oops. There's our final answer there. Okay, any questions on that one?
Could you go over why it's cubed again?
So if we put in all the units, let me write in all the units with it. So the 2, if it's kind of implied here, if dx dt is centimeters per second, that means x must be in centimeters.
Mm-hmm.
So that'll be 2 centimeters, and that's squared, and then are multiplied by 1 centimeter per second. So you get centimeters squared from the 2, and then you have another centimeter from the dx dt centimeters per second.
All right, thank you.
Mm-hmm. And you can just think about y. Y is x cubed. If x is in centimeters, then y must be centimeters cubed. And we're a rate of change, so that means it must be centimeters cubed per second. Okay, I think that is it for that one. Now the video, Dr. Sugar's videos, she had 2 videos going through these different examples and kind of showing the process. So I think, you know, we can do, I don't want to do them all again. Like, we're not going to have time to redo the entire lecture. So we have 2 options right now. We could go over 1 or 2 of these examples together more slowly. You can pause and interrupt, or we could find some additional examples. I am unprepared for today, so I'll probably just like try to pick one from the textbook or find one online. There's a lot of them online. I might have some actually in my old notes that I could pull up. And we could do a couple of additional examples. So I am flexible. Does anyone, I'm gonna get some stuff ready here. I think I might need to pause. I see an 11-year-old walking around my door. No, he walked away, so let's see. Does anyone have a preference for new examples or going over the examples from Dr. Sugar's notes? I saw
Can you go
some.
over problem 11 from chapter 4.1, the homework?
Okay, I may not have the homework up right now. How do I get the homework? Let's see. Hold on. I think probably the best way to get the homework is to go in the course page. So you got to be patient with me. I'm kind of trying to figure out the new, you know how like in class I always had everything ready and I had like screens on and I need this up and I got to be ready for this. And I am still trying to figure out exactly what I need to have ready. So I'm going to open up, oh shoot, because I do not have an actual physical text with me. So I think what I'm going to do is hold that thought and we will meet again tomorrow. So can we do that one again tomorrow, Christopher?
Yes, that's fine.
Okay, so let me find some examples from when I taught this class last time. Let's see here. Some of these might be similar to ones that Dr. Sugar had. That's okay. Oh boy. So it's just going to take me a minute here. I have them. I'm just trying to figure out how to get them where I want them. Okay, we're going to do page 53 to 57. Okay, almost ready. There we go. Yep, let's put them there. All right. What we just did. 57. Oh, we don't want that one. That one's like the hardest one. Try this again. I have, I think, 6 or 7 problems we can do here, and they kind of start simple and then work their way up in complexity. So let's try this again and see if we get the full list this time. Yeah, there we go. All right. So let's try, we'll start with a simple one here. This is now, when I say simple, that is a relative term. So I mean simple for this section. So not that this is an easy problem, but for this particular section, this is a relatively simple one. So suppose a fish jumps in a lake, creates a circular ripple. If the radius of the ripple it creates increases at a constant rate of 2 feet per second, how fast will the area of the ripple be increasing after 3 seconds? The key here for these is we have to start with some relationship. These are all about related rates. And so in our case, the relationship is the area. The area of the circle relates to the radius. The area is pi r squared. So often you'll have some geometric formula or some equation that you might have to make up yourself that relates the quantities that are changing. You have to have all the quantities that are changing have to be variables in here. So the radius is changing and the area is changing. So those have to be variables in our equation. If anything is constant, then you can just put that number in if it's constant. But neither of these are constant. The radius of the circle is getting bigger and bigger and bigger. Okay, now we're going to do just like we did with the paths from Dr. Sugar's notes. We're going to differentiate both sides with respect to t. So on the left, we'll have dA dt. And then on the right, we have 2 pi r, that's the derivative, but then r is not t, so we have to do the chain rule dr dt. This is like when I said in the practice, the study guide for exam 3, we use the chain rule almost every time now. We almost always use the chain rule. Does anybody have any suspicions for how we're going to answer the question?
We can plug in for, oh, wait, am I on? Oh,
Yeah.
we can plug in for DRT and
Yep.
what R is at that point.
Correct, correct. So r is not always 3. We don't want to put 3 in for r initially. If we put 3 in for r initially, all we're getting is the area at that moment in time. But r is not always 3. R is changing. So now if I
Would
want to
R
find the...
equal 2 feet per second?
No. So that's the rate of change of r. So let's, you know what we should have done initially? Kind of getting ahead of myself here. We should have written down what that 2 feet per second and we don't even know what the radius is, right? Because the t is equal to 3 seconds. If the radius of the ripple it creates is increasing at a constant rate of 2 feet per second, how fast will the area be increasing after 3 seconds? So that 2 feet per second, that's not a radius because it has the per second. What is that 2 feet per second?
The radius
Would
with
it be
respect.
dRdt?
Yeah, that's dr dt, right? Christopher is like the rate of change of the radius with respect to time. So that is dr dt is 2 feet per second. And we have 3 seconds, so we can plug some stuff in here. We can plug in the dr dt, that's 2, but we don't have r. Okay, so imagine here we have a little fish. It jumps, bloop, and then it starts creating these waves that get bigger and bigger and bigger. The radius is moving out at a constant rate of 2 feet per second. So what will be the radius after 3 seconds?
6.
6. So kind of just using your logic there. After 3 seconds, the radius will be 6 feet. So that's 6 in there. And then we just multiply everything together. 24 pi, and that will be square feet per second. square feet per second. The units, again, to kind of Christopher's point with our earlier question, 6 is in feet. Actually, let me just put those in a different color. You don't have to write units in the middle. You do need to put them in the end. 6 is in feet and 2 is in feet per second. So when you multiply those together, you get square feet per second. And let's do a calculator. I don't have mine with me. I don't have it up yet. Let's see here, 24 pi. So that's about 75.4 square feet per second. Lorenzo, go ahead.
What's the 9 pi supposed to represent? The one where you did pi times 3 squared equals 9 pi?
That was when I was originally confused that the radius was 3.
Oh, okay.
So that one is not applicable because when the fish jumps, initially, what's the radius?
2?
And no, not initially.
0.
0 initially.
Okay.
And then at 3 seconds, the radius will be 6 feet. And so at that point, the radius will be pi times 6 squared, which is 36 pi. But that's the area. So that really isn't relevant because we don't want the actual area. We want the rate of change of the area. So that, I don't know what that 3 squared was there. That was just me.
Oh, okay.
Yeah, I don't know. Me trying to teach kind of spur of the moment there. All right. Any other questions on this example? Okay, I am seeing none. So I'm going to scroll down. Okay, here's another one. Kind of let you read the question there. In the future, if I have prepared examples like these, I should email them to you. So we're kind of not an ideal circumstance right now.
For problems like these, in the future, are we going to have to draw our own diagram or?
Yeah, sometimes it's provided. Let me just scroll quickly and you'll see like sometimes I give it to you. Other times, like these two, I gave it to you. This one I did not. This one I kind of did. So it really depends. Sometimes you have to create your own picture to visualize what's happening, and sometimes it'll be provided. So what I like to do here on a picture like this, or a kind of situation like this, is try to draw, like summarize what, if I had to simplify this into one geometric shape, what would I draw? Like the previous one is a circle. The circle, the ripples are going out, it's a circle. If you had to simplify this to one geometric figure, what would it be?
A right triangle.
Trapezoid.
I see both of those because you kind of see him pulling here. So you can kind of see the trapezoid. But the key is that it's really just a triangle that's at play that's moving, because it doesn't really matter how far he is from that pulley. That really does, all that matters is how fast is he pulling on the rope. So it really is just the triangle. Let's see what's happening here. Let's label, what do we have here? We have a rope, so maybe I'll label that R. And then I'm just gonna label the other sides X and Y. Is there anything that's constant here that doesn't change?
8 meters from the dock.
I think, so is the boat always 8 meters from the dock?
Oh, never mind. No.
Right?
The
Right?
1 meter.
Yeah, what
is
is the 1
further.
meter? What is that, Haley?
The Y value.
Correct. You can see the dock is 1 meter higher than the boat. The dock is always going to be, so we could in fact just erase that Y and just put 1 meter there, because that will not be changing. That's always 1.
So is that like dy dt or no?
Well, no, that's a good question. So Y
Like it's
is
changing,
1.
right?
Well, is Y changing? That's the question.
Oh, never mind. Oh, it's because no.
Yep. So y, in fact, does not change. So y is constant. We do have at that particular moment, what is the 8 meters? What is that? The boat is 8 meters from the dock. So on my picture, what is 8 meters?
The X value.
X value.
X, right, Alexis? X. That's X. I also have this 1 meter per second. So don't say it out loud. Let everybody think about that. What is that that's changing at 1 meter per second? So give like 10 seconds here just to think about that. By the way, I ordered like a backdrop thing that I can put up in my office that I can hang a green screen. And then so the rest of the semester, I'm going to be having like very entertaining backdrops for the rest of the semester. This is really important, right? I have to teach from my office. I'm going to have like some cool backdrops. Because I tried to use some of the virtual backdrops and it just does not work with my lighting in here. Like if you do, has anyone played around with these? Like if I try to do this, it like, there's like more glare than usual here. It's even worse than usual. There's like weird stuff in the background. So yeah, not good. So I'm gonna get important purchase here. I'm gonna get a backdrop. Okay. Did anyone have any thoughts about? Chantel's shaking her head. Did anybody have any thoughts about what the 1 meter per second actually represents?
dr over dt.
Yeah. Can you explain how you knew that, Alexis?
Well, in the problem it says that it's a rate, and so it's the rate over time, meters per second.
And the key is rate of change of what? So we know it's a per t, and she said, hold on, that's the rope being pulled in. So that's the rate of change of that length of rope. There is one other modification we need to make because we need to be careful. Is the length of rope increasing or decreasing?
Decreasing.
Decreasing. So Brittany, you had your hand raised. Do you know what that means? Why I'm asking that?
Because it's going to be negative.
Correct. I can't tell you, like this is, once I go back to the classroom, I'm totally just bringing my tablet because I love how easy it is to change colors and erase and like, oh, it's just awesome. It sucks not being like in person, but you know, this is okay considering the circumstances. Okay, so the next step, I like it, taking time and writing down all the given information. Next thing is we need an equation that relates all of our quantities that are changing. So we have X and R are changing. We need an equation that relates them all. I should note here, Christopher said that this is a right triangle, and indeed it is. So we should note that that's a right triangle. So why don't you take 10 seconds and see if you can think of an equation that relates all of those things. And I'd love to hear from somebody who hasn't answered in a while. We have some lurkers today, which is fine. But if you have a thought here, you could type it in the chat or unmute yourself about an equation that you think that relates all of those. Anybody have any thoughts on that?
Can you use Pythagorean theorem?
Yes, you can. So that relates those, right? The normal Pythagorean theorem, A, B, C. We have a squared plus b squared equals c squared. And this is a common one. We use this relatively frequently to relate the sides of a right triangle. And so we can use that here, x squared plus 1 squared equals r squared. There's an equation that relates our quantities. Or if we simplify it, x squared plus 1 equals r squared. So if I'm highlighting steps, by the way, here's what I would highlight. Step 1, given information. Step 2, an equation. Okay, so now once I have that equation, don't want green. Any thoughts on what to do next? I've got my equation, I've got my given information, what next? How about Brittany?
Plug in the information you know.
Good thought. That is step 4.
Okay.
You are one step ahead of us. Alexis?
Differentiate.
Yes. So we have to get the rate of change. I'm like pointing at Brittany over here on the left. That doesn't really work. Sorry. We have to differentiate to get the rates of change. So that is exactly right. Differentiate. So we're going to do the derivative. And we're always differentiating with respect to t. I don't know if you remember Albert's earlier question about what the t represents. The t, again, I hinted then, is time. So we're always different. We have rates of change in this section. Everything rates of change, and it's always rates of change with respect to time. So we're always going to differentiate with respect to time. We're always going to use the chain rule for that as well. The derivative of x squared is 2x, but we differentiated with respect to t, so we have dx dt. Derivative of 1 is 0. dr dt will be 2r, or sorry, the derivative of r squared will be 2r dr dt. You can plug stuff in right now if you want to. We want to find, oh, I forgot to write that down too, gosh. Let's go back up to the beginning. What were we trying to find? How fast is the dock approaching? Or how fast is the boat approaching the dock? So what are we trying to find? Any ideas?
dx dt.
That's right, Haley. We're trying to find the rate of change of x. How fast is x changing? We might, this is really subtle here. But remember how we said r was decreasing because he's pulling in the rope? And so x will also be decreasing. So keep that thought. I don't think we actually want dx dt. It's very subtle. But let's finish the question and then I think you'll see what I mean. So let's go ahead and solve. I'm just going to plug stuff in now. You can plug stuff in later if you want. I don't know. Maybe we should solve for it. Let's do that. We'll just divide by 2x. So dx dt will be 2r over 2x dr dt, or r over x dr dt. Okay. We have a slight issue here. We have x. That's 8 meters. We have dr dt. That's -1 meters per second. We do not have r. So step 4, we're plugging stuff in, but we have a problem. We don't have r.
Can't you solve Pythagorean theorem by plugging in 8 for x to do 8 squared plus 1 squared equals r squared?
Yes, and I don't want to do, that's exactly right. I don't want to do that initially because that's not always true. It's just at that particular moment. At that moment, you have 8 squared plus 1 equals r squared. So that'll be what, 65 equals r squared. And so the length of rope will be square root of 65, whatever that is, square root of 65. And square root of 65 is almost 8. So this is almost -1. It's a little bit more, like -1.01. Yeah. -1.01 meters per second. And then my argument here is I don't think that that's the answer to our question. I don't think the answer is -1.01 meters per second because of the way the question is worded. How fast is the boat approaching the dock? I don't think it makes sense to say the boat is approaching the dock at -1.01 meters per second. Alexis, you have a thought?
You would change it to being positive.
Right, so dx dt is negative. It definitely is negative. But the answer to the question is it's really approaching at 1 meter per second. So let's do then, we'll call it step 5. Oops, I did gray instead of green, that's okay. The boat is approaching the dock at about 1.01 meters per second. Okay. Any additional questions on this additional like extra example here?
What was the purpose in turning the 1 into negative when we were going to just turn it back into a positive at the end of
I
it?
think the key is we want to make sure that if we've drawn, we want to be precise and correct in what we're writing, because different problems might ask different things. And so if we're going to call it dx, if we're going to call it dr dt, r is getting smaller in the problem. So since r is getting smaller, dr dt should be negative. In another problem, like it really, you want to make sure that the symbols you're writing are correct. Now it happened in this case that we made the answer positive in the end. And so if we had ignored that and left it positive initially, we would have been right and it would have worked out. But another problem, it might not. So we really just want to make sure that the statements we're writing, especially this statement here, dr dt, that it is correct and it is decreasing. It is definitely decreasing. That might, you know, like in this, to your point, in this case, we ended up making our answer positive anyway, but that depends on the problem. Different problems won't do that. So we just want to make sure we're writing the correct sign. Because other times we might, here's a clear point. Other times we might want to know, is x increasing or decreasing? So we would need to know, is dx dt positive or negative? And we would need to have the right sign on dr dt in order to answer that. I don't know if that's a little more convincing, but. Any other questions on that one?
Why didn't we plug in the 8 initially for the Pythagorean theorem again?
Yeah, that's a really good question. It's a really common question, and it comes up a lot. The issue is that when we're in step 2 there, we only want to plug in stuff that is constant, if it never changes. Because in step 3, we're going to take a derivative with respect to t. And if I've plugged in 8, I have this equation over here. And so the derivative on the left-hand side is just 0.
Oh, okay, yeah.
Right? So we only plug in like kind of at the end.
Mm-hmm.
Yeah. So anything that's changing, we want to leave as a variable initially there in that earlier part of the process. If something's constant, like the height of the pulley from the dock, you can go ahead, plug it in, put in that number if it's constant. If it's not constant, we want to leave it a variable. That is one of the like really common thing that people struggle with in this. So it's a good question. I'm glad you brought it up. Any other questions? Okay, if you have not yet watched Dr. Sugar's videos for, there's like, was it 4 examples total? Is that right? I can't remember. Watch those for tomorrow. Tomorrow we'll come again and we'll do some more examples. And then we'll have, because I have some more here. I'll try to get this, I'm gonna make a note for myself. Get some more examples uploaded. So upload PDF of related rate examples. And this is my vision for how we'll do these classes. We're going to do them twice a week, remember, moving forward, just because of my time commitments with grading and everything else, where we will answer some homework questions. And whenever we're done with homework questions, then I'll have some extra examples, but we will usually not be like doing a bunch of notes. That's what the videos will be for. And so I'm hoping that this kind of just doing lots of examples will be a useful time. So tomorrow we'll meet and we'll do some more related rate examples, some more from this handout right here. And that'll be your task for the weekend, will be to work on that homework and then watch the videos for 4.2 over the weekend. If you want to work ahead and watch like a couple sections worth, if you're during the week gets a little crazy and you want to have those notes done, you know, we're a lot of flexibility there. What I'm going to do is I'm going to try to be really clear about make sure you've watched, you know, X videos by Tuesday. You know, just so make sure you've watched. That's kind of what we're going to be focusing on. Yeah, I think that's it. Any other questions today about anything? All right, I am seeing none. So I am going to end the meeting. Thanks, everyone. Where's my end meeting? Thanks, everyone. And I'm going to do my best to be grading. Today's going to be a busy day trying to grade. I don't know how long logistically it's going to take me to grade. with the new format and everything. So I'll try to get, I know you're anxious to get your exams back. I will do my best. I'm not making any promises whatsoever because this is my very first time grading in this format and I have no idea how long it's going to take. So I will see you all tomorrow. All right. Bye, everyone.